Hello everybody, welcome to the lecture 6 of Algorithms and Data Structures course. Today we're gonna learn sortings. Mainly merge sort and the quick sort. That would be our main algorithms for today. And we will recall some quadratic sortings, and then we will see how this merge sort and quick sort works. This is very interesting algorithms, quite a tricky ones. And then we will see what's the asymptotics of those algorithms, and we will show that any sorting algorithm, the best we can achieve is big O of n log n, assuming that we only allow to compare the objects. So let's see. So in general, the problem looks like this. So we have So the general problem, as an input, we have n objects and comparator for these, and the comparator for these objects. Comparator is the function that takes two objects and says who is larger and who is less. Okay, so we are given n and some objects a1, an. In our case, that would be in integers for the simplicity, but in general, you can do anything, and like you can have any objects and compare them. Only thing you need a comparator. Um, so comparator is a function of two arguments, like two objects, that returns you true if x not more than y and false otherwise. So comparator actually just means the Boolean output of this Boolean term of this Boolean term. Oh, I'm sorry, of this Boolean term. So that term, that not more or equal is actually not necessarily what you're thinking of it. So these guys are not necessarily numbers. For example, if there are strings, then the inequality might be different. So by saying that, I mean that um, this sign, this is the relation, which is called order relation, and must be a total order. So less than or equal here means any total order, even decreasing order. For example, I can say that this sign means x not more than y when x larger than y, and vice versa. So I can invert it, and only I need from this sign, from this operation, from this Boolean operation, is to be defining a total order. All right. For example, for the strings, the way you can compare the strings is you can compare them letter by letter. So let's say we have two strings s and t. So you first compare the first letter if they are equal, or then we compare the second letter if they are equal, and so on until we reach some moment when two symbols are different, and if this less than this letter comes in alphabet, um, appears in alphabet earlier than this letter, then string s is less than string t. Otherwise, string s larger. If this moment does not occur, then it means that um, this string is substring of this string, like a prefix of this string. So if it's empty, symbol, like there's no symbol at the top of the s, then s is less than t. This is called lexicographical order. Lexicographical order. This is the order which appears like that as alphabetical order. Lexicographical order. Lexicographical order. I'm sorry for the writing. Lexicographical order. So there are a bunch of orders. You can order them not by. You can order strings by the length. That would be comparison of the integers. You can order strings by, I don't know, by number of vowel letters or number of A letters and so on. So the comparator can be anything. You can even compare strings by the digits, or you can even compare numbers not by who is larger, which number is larger, but um, uh, by digits as a strings. So that could be a case as well. Okay. So in this problem, so yeah, the output must be a sorted array. I want to sort the array with respect to this specific total order, as I told you before. So note, in this problem, we are only allowed to compare two elements. So with only one operation, comparison of two elements, uh, what is the minimal amount of operations we need to do to sort the array? That would be a question of our interest, and we will see a different approaches to it. So simplest, these are the sorting algorithms. So there are classified in two ways. So one first class is the simplest class, is this quadratic sortings. So they are quite simple. I will show you in a moment, one of them. I'll show you bubble sort, insertion sort. Insertion sort is basically you're given an array. So what you do, you just create a new array, and each time you insert an appropriate place. So like you have each iteration, so you do n iterations, and each time you have array at ith iteration. I'm sorry, at ith iteration. Maybe I should close it for a moment. At ith iteration, what we do, we have an array, we have a sorted array a1 ai, and what you do, ai plus 1, you want to insert yet another number to this array. You just linearly search the position where, not ai plus 1, let's just say we want to insert x. Just search for the position where, let's say this satisfied. Let's say this satisfied. I and ai plus 1. J and j plus 1. You just search for this position and just put x and j plus 1. Like, then you find this position, you shift everything to the right of this position, by one position to the right, and put x into the gap. Okay, that is the simple algorithm. You don't actually need to, um, it is not hard to understand, right? This is just straightforwardly doing um, what is required. Okay, bubble sort is a bit more, um, is a bit less trivial, I would say. But still, this is big O of n square asymptotics. Yeah, so what we can do better actually. We can do big O of n log n operations, which this category of the algorithms are called fast, uh, of sorting algorithms are called fast because you cannot attain nothing better than that. So there are heap sorts on the previous, and at the end of the previous lecture, we already had the heap sort. Um, so we know this one. You remember, you build a heap you take the array, you build a heap on its place, and then you remove the top elements one by one until it is empty, like until heap is run out of the elements. So that would mean that array A is sorted. Okay, the um, merge sort and quick sort are a bit trickier. So the merge sort based on the idea, like a general idea, which a lot of algorithms rely on. Merge sort does divide and conquer method. So it is like a category of the algorithm, like the algorithm in the category of divide and conquer. So binary search is kind of like a divide and conquer, as you remember. So you divide your segment into two parts. So you divide them, and then you decide which part is better for you. So you conquer it. Okay. So this algorithm now, merge sort, is actually also a divide and conquer method. Quicksort is a very funny algorithm, and it is actually, um, we could say that it is divide and conquer as well. Okay, So before that, let us see the bubble sort. This is these 4 lines of code is actually the algorithm for the bubble sort. So entire this is the sorting. This is the entire function of the sorting. So this is all the code. So what it does k iterations, or it does n minus 1 iterations. Each time you do the following, you just move through the array, you move from left to right, and if you see that ai is less than ai plus 1, then you will push it, or larger than ai plus 1, then you will swap those elements so that at this position inequality is okay. Okay, then you swap them and you just swap it till the end. So the exercise for you guys is to prove it. Show that this algorithm works. So you do this iteration. So you do this transverse, like not transversal. You do this walk over the array n minus 1 times. Actually, one can know that we can say here even this n minus k. That would be still big O of n square algorithm. That would be still n square algorithm because you can calculate how many times these two loops go, and that will be up to a constant n square. Okay? Yeah, prove it. So now we go right into the merge sort. Merge sort is recursive algorithm, which is like most of divide and conquer methods are recursive. So the algorithm looks like this. So it actually consists of 2 parts. So let us see these 2 steps, simple steps. So initially you have this array, 275316. First step is divide. You split them into 2 equal parts, maybe plus minus 1 equal parts, and then sort them. Okay. You sort each part independently. After you've done that, um, so after you've done the sorting, you do the merge. So the next step is the concur these 2 lists. So now you can use the fact that these 2 lists are sorted. So you see there is increasing order of these parts, and your aim is to merge them into the single list, sorted list. Okay, and we can do that. So since they are both of equal size, uh, no, not necessarily they are both. We will see how to merge them. This is actually like a separate function merge called merge. We'll see how to merge them in linear time. So in big O of n time, assuming that this is n over 2, this is n over 2, and n is the length of the initial array. We'll see how to do that in big O of n time, but in general, merge can do just merge of 2 arbitrary arrays of arbitrary lengths. So we have array of length A, sorted array of length A, sorted array of length M, which is called B, and merge will give you, so with merge, you will obtain array of length M plus 1, M plus M, like made up of these elements from this union of these 2 arrays, but in the sorted order. And that would work big O of n plus m time. That's the idea. The algorithm looks pretty much like this. So we first understand the recursive part and then understand how to merge. Okay. So recursive part looks like this. So if L equals, so we have some M sort stays for merge sort. You have 3 parameters: is the array, like the pointer to the array, the left and the right, like the left and the right. So LR means the segment you're gonna sort, the segment you want to sort. So initially, so when you are in the main, you want to call msort merge sort A and 1n, for example, or 0n minus 1, depends on your implementation. Okay, so now what you're gonna do. Mid is equal to L plus R over 2. So you take the middle, so you have a segment, and you take the middle. You take the middle element. You say that you sort this part, the left part, so middle element is the uh, right boundary of the left segment, of the left part, and mid plus 1, so from L to mid, and from mid plus 1 to R. Okay? So you sort this, and now you just merge. So A L mid, A mid plus 1 R. So it's just this part, and the destination where you want to write it. Maybe even that not that that is not necessary. I will show you we're gonna implement that a bit differently. But the recursive part is all this. Let us see step by step how it looks like. Okay, so uh, let us show how it looks like step by step. So yeah, this is initial array. So we kind of what we do. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So initially you have array of like 9. You split it into the two parts. So 9 plus. Oh, I made it wrong actually. 9 plus 1 over 2 is 5. So that would be like this, and this part would be these bounds. But okay, this doesn't matter. Like in the code, you're gonna do not here. This line is gonna be not here but here. But I'm not gonna fix that. This is almost the same. Or I can even change the code so that this part would be always larger than this part. Okay. So, oh, finally they finished. Okay, so sorry for the noise. There is a um Stroika, like Remont in the university, repairing uh, room repairing works in the university. So what we do, we we want to sort this. Okay, so we initially had this array, so we split that into two parts. Then we take left part, then split it again. We take this left part, split it again here and here, and then when we will come back, so we actually each moment of time. So since it's recursion, we can draw a recursion tree. So initially recursion tree stays at this stays at the state 1 9. So 1 9 is the kind of like a state of our recursion. So this is the segment which we are on. Now we split that segment into two parts, 1 4 and 5 9. So first of all, he is gonna go here. He's gonna sort this segment, then it splits it again, then it splits it again, and so on. So now, first thing you're gonna do, you're gonna climb up back to the segment 1 2. I'm gonna sort it. Okay, I'm gonna write the sorted newly sorted elements with blue color. Then we come back here. When we go here, split it to 1. We sort them with merge sort. We're gonna have 1 2. Now we're gonna have this segment. So we erased it. So we have two lists with sorted values, and then we're gonna um, unite this into the single list. So how are we gonna do that? Um, how are we gonna do that? So the way we're gonna do that is we take so um, this is actually I wrote it here. So the idea would be the following. So what we have the state. We have two arrays of different lengths, maybe different lengths. It's not necessarily different. Maybe it is equal. Maybe it's not. Doesn't matter for the merge algorithm. So like for the merge function, we're gonna implement the merge function. Oh, sorry. We're gonna implement merge function, which is going to be working like this. Um, which is going to be working like this. So let's say we have two arrays, 1579, 24566, okay? This one and this one. And so we're initially gonna have two pointers, I equals 0, j equals 0. So these pointers, I is for the array A, G is for the array B. What we're gonna do, we first, so like, we wanna obtain the union of these two arrays with the sorted order, right? So who is, this is the minimal principle, minimum principle of the minimal, principle of the, принцип крайнего по-русски говорят. So we're gonna think of this like that. Who is going to be, which element is going to be the minimal element? So the first element in the sorted array. It's definitely one of those two, because two is least number in this array, one is least number in this array, and this guy is gonna decide, they are the finalists for the competition of who is going to be the first in the C array, in the resulting array. So we just compare them. It's one or two. It's one, of course, in this case. It's one, of course, in this case. And what we're gonna do, we're gonna put that into A, into C, and move the pointer. So this is actually what is written here. So while until it makes sense, I'm gonna reveal the details in the code. So I'm not gonna do that straightforwardly right now. And then we're gonna ask if AI is not more than bj, then we put AI like at the top of C, so as a stack. If you think of C as a stack, then I put it at the top. Actually, I just add it at the end, at the current end. Okay, and move the pointer I. Otherwise, I put bj and move this pointer as well. So there are other cases when I and j is gonna run off. I'm gonna discuss it with you right now. So now I'm comparing 2 and 5. I put 2 and move this pointer. Now I compare 4 and 5. I move this pointer and write 4 here. Now I compare 5 and 5. In case of equality, I decided that I'm gonna put A, so I move this pointer. So, but actually it doesn't matter. Then I put this 5 here as well and move this pointer. Now I compare 6 and 7. I move this pointer and write here 6. Now I compare 6 and 7 again. I write 6 and move this pointer. Now the pointer is out of the range, and it means that known elements left in B, so it means that all remaining elements can be just written down here, 7 and 9. Yeah, now we get the sorted list, like the union of this merge of these two lists. And what I've skipped here is actually essential cases. These are the cases if I is equal to n, if j is equal to m. So if they are run out of the numbers, so if the pointers are actually run out of the run out of the array, so it means that no remaining elements left to insert into the C array. If so, you should actually like consider these cases as well here. But this is the core idea, and there are technical details. I'm gonna write. You're gonna see how it works in the code further. So finally, coming back to our recursion and step-by-step example. Um, so we know now how to compare them. So we compare 1 and 4, we write 1. We compare 2 and 4, we write 2, 4, 8. Now, okay, we done here, we go here, we sort this. Now we sort this, we sort this. So when it's one element, we don't need to sort anything. Now we, again, compare 0 and 9. Oh, too large. Compare 0 and 9, write 0 and then 9. Compare, then we want to sort this part. 7 is okay, 6, 5 is not okay. We're gonna write 5, 6 here. And now we're gonna write, and here we're gonna write, we compare 5 and 7. 5, we can 6 and 7, 6 and now 7. And now here we compare, now here we compare 0, 5, we write 0. We compare 0, 5, we write 0. We compare 9 and 5, we write 5. We write 6, we write 7. And finally we write 9. And to compare these guys, what we're gonna do, we're gonna compare 0 and 1, put 1, 5 and 1, 1, 5 and 2, 2, 4 and 5, 4, 8 and 5, 5, 8 and 6, 6, 8 and 7, 7, 8 and 9, 8, and we just write 9. And finally, we got the sorted order of numbers. So we sorted the numbers as we wish. So basically what I did, I just traversed this tree, and whenever I leave like before I leave the vertex, I do merge of these two lists, of the lists of my two children. All right, that's the merge sort. I hope this is quite clear for you. And um, let us uh, let us go to the implementation. Okay, let's implement merge sort, and then we will go to the then we will jump to quick sort. Okay, so the merge sort function would be looking like this. I replaced LR with just, we don't need actually LR. We can have a pointer to the beginning of the array and M. So from the global scope, or from the main scope, that will be looking like this. Oh, that's not how it works. I guess 9. Uh, and let us try the array from the input, from the example. 2 1 9 9 0 7 6 5. That could be actually anything, but we'll do this. We will take this example. So we will call it like this. Merge sort this. Okay, so now what we're gonna do? We're gonna split it like into two parts. The way we're gonna do that is we're gonna take, okay, the left part would start at A, same as the initial array, and that would be of the length n over 2. Okay, and then we sort the other part. That would start from A plus n over 2. Yeah, here we're gonna have zero index based base sort. We will follow the standards because um, in C++, for example, and all the other programming languages, it usually starts from 0, and you need to specify the 0 index array, like the pointer to the 0 index array. Usually in the C++ sort, you do something like this, AA plus 9. So you specify the left and the right pointer, like the bounds, which are the pointers to the array. So the start of the array and and the end of the end of the array, which is not included. Okay, pointer to non-existing element. Like end is always non-existing. That's usually like this. We're gonna replace that with the length. Okay, so our array actually A0, A1, literally those elements is of our interest. We're gonna sort these elements. Okay, what we're gonna do, we merge sort A n over 2, and the new array starts from this. And in case of odd number, I can put n over 2 here as well, but in case of odd number, for example n equals 9 as we have initially, 9 divided by 2 is what? Is 4. So it's going to be 4, but this is going to be 4 as well, so we should probably do n minus number 2, the remaining part. That would be 5. Here would be 5. And then what we're gonna do, we're gonna do merge of these two parts. Left part a n over 2, and the right part is this one. All right? And we will want merge to write the result to the array starting from A, and n elements starting from here, from this pointer. Okay, that's it. That's the recursive part. That's the end of the recursive part. So now we do merge. Um, int a, int n, int b, int m. If you are wondering what is point array plus n over 2, so remember that the array is just a pointer to the first element. So here a is just a pointer. So here a is a pointer to a0, right? So whenever we say a of 9, a of 5, for example, what we actually do, like literally what we do, is we're saying that we take the pointer a, move it 5 cells forward, okay, and take the value of this element. And maybe we take address of the of the of the element, like something like this. So we take the the value, this is taking the value, and this is taking its address, so like real address, so that we can say like this is not equality, I mean this is like this is equivalent things. So the way this ampersand here is that we want to take the address so that that would be editable. As I showed you in the previous examples, in the previous implementations, this were used for make to make like for example to make variable changeable. I mean when you pass the address, then it means that when I say a5, I can say a5 equals to 5. Then what that would mean that into the address which write this like the into that specific address in the memory, write 5. Okay, all right. um, Perfect. Now, then what we're gonna do, we're gonna implement the merge. Um, the way we're gonna do that is as we discussed before. So I equals 0, j equals 0. So we have the pointers to the elements of a and b. And now we do, now we need some container for the result. That would be rewritten, we will rewrite uh, at the A. So, but before that, we need some container. That would be C. Sometimes we can do that in the global scope, but to be um, more consequent, we will do that locally. So that will be array of length n plus m at the end. So at the end, after everything we've done, after the merge is done, we're just gonna rewrite everything which is in the array C, CZ of C, or that would be n plus m. Um, we're gonna write just AI equals CI. So here we even can assert that um, um, that the size of C is equal to n plus m. So now we're ready for doing, we're ready to do like a real merge. So this while loop goes until so while A is not equal to n and I is not equal to m. So while one of them is not fulfilled, so uh, while not all the elements are processed, or not I, j here, while not all elements are processed, I'm gonna ask first if um, I equals n. In this case, I do, if I equals n, I do c dot pushback. So I put at the end of c, I put bj. So like if the left array is already processed, I just need to process the right array, right? J++. This is the fast way of saying, okay, do this and do this. So let me emphasize that somewhere here. Um, so like AI++ is the same as AI++ equals, or maybe c dot pushback AI++ is the same as c. Oh, PB is not what I wanted. pushback. Let us say it like this. This is usually a short. There's usually a shortcut, but I'm not doing it here. Okay, c dot pushback AI and AI plus plus. This is basically this. So this and this is the same. So I'm gonna write the fast version if you are not against of it. So if I this else c dot pushback AI plus plus, or else if j not equal to m. So if we didn't reach, oh, vice versa. If the right one is empty, then I just need to write down the left one. So that is the case. Remember when you, for example, reached where it is. Yeah, when we reached j here, we put it 7 and 9 automatically. And that is exactly this case. J equals m, j equals m. I put the remaining elements of the left array into the C. Else, this means that A is less than M and J is less than M as well. In that case, what we're gonna do? We again compare. And the way we compare is the following. So we now compare like a basic thing, like this, what is on the right side. AI is less than BJ. We now know that both of the arrays are not run out of the elements yet. So we ask then if AI is less than BJ, then I do what? 1, 2, 3. C dot pushback AI plus plus. Else I do C dot pushback BJ plus plus. Yes, there are repeatings of this and this, but that is necessary. You actually can, mm, you can write it within single if-else clause, but this way it is more, um, it is less complicated. It is, yeah, it is much more readable and clear. So yeah, at the end, I'm gonna add, so each iteration of the while, I just add one element to the C array, all right? And totally, this while loop will work for m plus m operations. That is why the asymptotics for the merge is O of m plus m, all right? And at the end, I just rewrite it. Okay, so let us try merge. A of I, and maybe I should write int n equals 9 here. Like for the future. Okay, let me try this. G of m dot out. What? Wait a sec. Oh, where did I write this? Oh. I messed up the files. Okay, I'm gonna fix that now. Um, yeah, this says something is bad. Oh, okay, so the CZ of C is no Dutch function, but there is a C dot size, and C was not declared in the scope. What about this? There's no vector included. Okay, include vector. Oh wait, here it is or. It must be or. So while I less than n, we can actually write less or not equal. Less might be a bit more convenient. If I is less than j or j, if one of them is not run out of the elements, then we do the steps. So now it is sorted, as you can see. Okay, so we figure out the asymptotics of merge, but we didn't speak about the asymptotics of the merge sort in general. And the way we're gonna do that is that um, how many like observe that this recursion tree, each step of the each recursive call of this m sort function is actually some vertex of that tree, and that tree is a complete binary perfect binary tree, right? So like complete binary tree, and it is balanced, of course, because each vertex has almost equal sons, or equal length sons. Okay, so we can say that the number of levels here is logarithm of n. So this is the first level, second, third, fourth, and fifth. Okay. Um, this is going to be proportional to the length of this array. Or we can, yeah, the fifth. So 5 vertices here. And that is actually a logarithm of n, maybe plus 1. Or maybe, yeah, 1 plus logarithm of n sailed. That's going to be something like this. If you include this as a level as well. And on each level, what we have on each level, we have linear number of operations. As you can see, for example, at this level, what we have here um, linear number of the operations. Or maybe, no, this is the bad level to show. For example, at this level, for this state, for this subsegment, we do linear number of operations to merge it, right? So the merge on each iteration, what we have, what contributes to the time complexity is this function merge, right? Because okay, this is the recursion, this is the recursion, and that is O of n, or specifically in this case, if we replace this with n, we can say big O of r minus l plus 1 or big O of n. So n is the length of the array at this state. So each time we have linear number of operations, and so linear number of operations here, linear number of operations here, but the width, like the length of like the entire array is n. So on this level, we're gonna have like this is n, this is 4, let's say, this is 5, let's say, and so entirely it's gonna be 9, right, in total. And that idea can be applied on each level. Here we have linear number of operations of this length, of this length, of this length, and of this length, and in total that would be the entire length of the array, right? So on each level, we do linear number of operations. Here it's O of n, here it's O of n, here it is big O of n, and at the bottom level, we don't do anything. Maybe here, but that's not counted. Okay, maybe here, okay, big O of n. So if you break down each recursive call and count um, how many operation merge does on each recursion call, you will see that on this level it is big O of n. I'm repeating myself, but in this level it's big O of n, on this level it is big O of n, and so on. So, but the height of that tree is logarithm of n, so that be log times big O of n. So in total, we're gonna have big O of n log n number of times. That's it. So if you want it, this is the way I mean, this is quite um, um, quite strict, like quite exact estimation. I mean, this is there's no something wrong about it. This way, you actually can say that this is big O of n log n. Another way we can say that it is big O of n log n is actually to calculate number of operations recursively. So T of n is actually would be what? So we split the array of length n into two parts, n over 2 and n over 2. So this is 2 tn tn equals 2 tn over 2 plus, and we do merge, which is linear in the length, big O of n. That formula produces big O of n log n time. Okay. Okay. So um, that is merge sort. We're now gonna study what is the quick sort. Let me give you a few moments. Give me a few moments, please. Okay. So suddenly pictures appeared. So merge sort um, is, so let us take the array and draw it on the xy plane so that the points at position, so we embed these elements by like this. So element I at position I would have coordinates I and A of I. So that would be like bars, or like the strips, that is the bars of the array, representing the array. And what we do by the merge sort, we split these bars by like a vertical line, then sort left part, sort right part, and then merge them each time. So the quicksort algorithm is almost the same. Idea is similar in the sense that we're gonna do that almost. We're gonna do that by the y-axis. We now draw a horizontal line, um, split these elements. Yeah, we're gonna draw a horizontal line, split the elements to the top and to the right, so that that would be two equal sided. Um, um, so we're gonna draw such a line that the number of points above that line would be n over 2, and number of points below that line is going to be n over 2 as well. So that so then we just split this array, like our array, in such a way that they will cover. They would be like those who are above the line would be a consequent sequence of the elements, and the same thing for the for those points who are smaller than this line. Okay, so the condition of being above or less than this line. So if this line is equal to, like, let us denote it as m, then we just need, then uh, these guys, top points are those who are larger than m, and uh, bottom points are those who are less than or equal to m. Okay, so the idea would be the following. We'll find such a number, such a line that splits our array into two equal ranges, and then we rearrange the number. So that would be, for example, exactly in this case, this, and this is not it's not a subsegment, right? It's not a continuous, it's not a contiguous sequence of the elements. So there is a gap between them, right? So this gap between two elements, or for example, for the bottom part, there is a gap between these two elements. So, but the idea is that we're gonna pick the element so that it splits uh, this set of points into two equal sets, and then do quick sort on separately here and separately here, and um, in particular, what we're gonna do, we're gonna wait, where it is? Oh, in particularly what we're gonna do, we're gonna select certain elements and then rearrange the elements of the array so that we pick the element m. Oh, sorry, we pick the element m so that and then rearrange the elements in the array. So we pick some element m. These numbers and these numbers are not yet arranged, and then we arrange them so that numbers that are less than m will be to the left of m, and less than or equal to m would be to the left of m, and larger than m would be to the right of m. Okay, and then we do quick sort on both of these halves, and not halves apart, but parts. But we want them to be of equal size. And actually, such an element is called median. So the median of an array is the n over 2th element in the sorted order. So for example, you have this array, you sort them, then 3 is the median, but it's not necessarily in somewhere in the middle. It might be like here, it is at the end of the array of initial array, but this is the median. Okay. All right. So the idea is to do divide and conquer by values. So not by the, but in the merge sort we did divide and conquer by the indexes. So we split into two equal halves uh, by using the indexes. Okay. Now we use the values for that. So we take the median and arrange elements to the left and to the right. But the problem is here that to find the median, you need to sort the array. So there's no way of finding a pivot element faster than n log n. Oh, not pivot, median element that is faster than n log n. Okay. Uh, yeah, and that is not suitable for us. But we will deal with that. We will think of that. We always find the median, but let us call not the median, but the pivot element. In case it's not the median, we call that element the pivot element. So this is the pivot. This is the pivot. Pivot means опорный элемент. Ключевой. So we pick up some random. So what we're gonna do actually, we're gonna pick random elements and think of it like it's probably a median. Okay. And I will explain why it's gonna work. Here's the pseudocode. So again, recursive part first, and then the core of the algorithm. So quite simple. Q sort stays for quick sort. A is an array, L and R are the range we're gonna sort. If L is larger or equal to R, then we just return, nothing to do here. Now we ensure that L is strictly less than R. So in case L equals R, we're okay, and we will see that here it might be L larger than R, so we're gonna return it as well. So if there is no array to sort, if L and R are not suitably placed, then we should return it as well. So we now ensure that L is strictly less than R, so there are at least two elements in the range. So now what we're gonna do, we're gonna do partition. Partition selects the pivot. Partition function is the function that selects the pivot and then arrange elements to the left and to the right according to this picture, and return the position of the pivot. Okay, if only if we could have find the median fast enough, then that would be always the middle of the of the um, of our segment LR. But we can't do that. That's why we just just remember which we do partition and then remember which element like on what position pivot is. This position. So, and then we do quick sort from left and right side. Okay, so the most interesting part is the partition. How we're gonna do that? Let me explain it on the paper, and then we're gonna write it on the board, and then we're gonna implement that quickly. Okay, so we have an array. This is L, this is R. What we're gonna do? We're gonna select pivot randomly. Pivot. Okay, first step is pivot, random pivot. First step is random pivot. Steps is random pivot. The second one. So we selected the random pivot. Then we put it at the end. We swap with the ends. swap with the ends. Um, we swap with the ends. Then, so now pivot is here. We can forget about this guy, this thing, or maybe, oh, okay. I just wanted to write it in with a different color. Okay, this is the pivot. This is the guy we are comparing with. Okay, step 3. We run from we run from left to right, run from here to here, from here to here, from left to right. We have what like the pointer we're gonna running, so there is a for loop, like for j from L ta 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 to r minus 1. As soon as L is less than r, this L is strictly less than r, this for will make at least one loop. You see here we have this condition. So now what we're gonna do, we ask if a of j is less than a pivot, or maybe less than or equal to the pivot, we will throw it to the left. So we're gonna have a pointer I, which is initially L minus 1. So I would be pointing, so what I'm gonna have, like each time I'm gonna have position I, so j is somewhere here, and j is somewhere here, and each time I'm gonna measure, I'm gonna remember last position of elements who is less than or equal to m. Okay, and then I'm gonna increase this. I'm gonna move this pointer to the right as soon as j is moving right to the right. If j is hitting the element which is larger than this m, that our pivot element, then we're gonna leave it in its place. And if it's larger, then I'm gonna swap it with this guy. Okay, I'm gonna put it at the I plus 1's place and move the pointer to the right, like increase the size of this range. So basically what I'm doing is I plus plus and a of I, swap a of I and a of j. So the reason why I initially is L minus 1 is that initially we don't have any segment of less than or equal numbers. So initially, if the first number is less than or equal to m, if it's less than or equal to m, I is pointing here. I'm gonna move pointer I to the position L. So this is position L to the position L. I'm gonna move pointer I to the position L, and then swap it with itself by the code. Like if you look at the code, I'm just gonna swap it with itself and then proceed j here. If it's less, I'm gonna swap it with itself again. If it's not, I will leave it here and move the pointer j now here. If it's less than j, if it's less than pivot, then I swap it with this guy. Since this guy is already, we know that this is larger than m, it doesn't matter where it lies. So we use the fact that we don't care what's the order inside of this partition of less than or equal to m or larger than m. We don't care about the internal order of these guys. We only care that they're going to be to the left and to the right of them. But I mean, at the end, we're gonna put it in between them. But for now, we're gonna just stick them together and see that okay, they are um, and just we're gonna like partition them. Okay, at the end, what we're gonna do, I'm gonna put pivot at its place. So uh, let me say swap with the end. Uh, let me say do partitioning, do partitioning, and this is the hardest part. And then at the end, I just put pivot between partitions. between parts, let's say. So I'm going like this. I'm gonna put it there, here and there, and then at the end, I would have some partitioning. Let's say like this. Let's say this is finished, and I got this kind of partitioning. So from here to uh, from here to here, it is larger than m, and from here to here, it is less than m. So I just swapping this guy. I know this pointer I store it. I remember it. I swap I plus one guy with with last element, with the position R element, swap it with him, so that now it's going to be like this. So I plus one, and from here to here, this is larger than m, this is m, this is less than or equal to m. Okay, that's it. Because again, the order in which larger than m part elements are ordered, so the order inside of this part doesn't matter. So I'm gonna write it. I'm gonna write it like this. If what? No, not if. Swap I plus one and AR, and then say return I plus one. So now that I can increase like R minus L times, right? So this would be, in worst case, I would be R minus one. So I'm not gonna swap with itself. So I is going to be at most R minus n. So I plus one will be still in the range. So that is also important, which is it is seen from the code that that would be in the range. Oh, sorry, this is the not here, but tab issues. This is here. So that's the function of partitioning, and that's it. Wait. Получилось. Нет. Короче, ладно. Окей, so, давайте, ладно, вот так сделаю. Черт с ними, с этой стрелкой. Стоит на место. Okay, so this is the function partition. ALR. And here I say that I choose the pivot in some way. Choose pivot. Like pivot equals A of rand modulo R minus L plus 1 plus L. So that would generate me the random number from the range from 0 to R minus L. Okay, and I'm shifting it to L and then take the elements. So I'm taking, basically it means that I'm taking a random element in this range. Okay, and the asymptotics of that algorithm is actually, it is not straightforward to see. Okay, if suppose that I'm always selecting the median of the array. If I'm always selecting the median of the array, then it means that if I'm always selecting the median of an array, then it means that each time I'm gonna split my array into two equal parts. That will be again the formula T of n equals 2T of n 2T of n plus big O of n for partitioning. This is partition. Okay, T of n over 2, of course. These guys are for the recursion, so the left and the part right, sorting the left and the part right, and then do partitioning. This is again big O of n log n. But that is not the case if I if I do it randomly, it does not necessarily be the middle element. But one can prove that a mathematical expectation, mathematical expectation means that number of operation sum over the number of operation times. So mathematical expectation. So let me write the formula for those who understand the formulas. So it means that probability of like T of n is equal to x times x. So this is the like average weighted of all possible outcomes. Okay, of this is sum over x possible values. So this is mathematical expectation and denoted usually as yeah expected. Expectation of T of n is equal to big O, not big O, like in average that would be n log n again. Like this is usually called sigma n log n. Or not sigma, this is omega. Omega means in average. So if big O of n means in worst case, this means in average. Look, I actually wrote it incorrectly. This should be a different line. Just T of n is equal to this. And that would be, because our algorithm is probabilistic in some sense, then the expected number would be actually big O of n log n. So in average, that would be n log n, and it's very rare that your algorithm would work n squared number of operations, okay? This usually works fast because nobody can trick the randomness of our world. In contrast, consider the case if I do not random here. Let us say that we replace this line. What if I replace this line with not picking a random element, but I'm gonna pick the always, for example, like the media, like the central elements, or the last elements. What happens then? Is it going to be big O of n square? Is T of n is big O of n square in this big O of n log n in this case? That is the question I'm gonna address you during the question and answer session. This is an exercise. Figure out if yes, then prove it. If no, then provide the example. Provide the case when it's going to be n square operations. Okay, for example, this case or for this case. Okay, so let's jump into the implementation. We're gonna create new file q.cpp. That would be this. Let us leave the array as it is. Let us replace it with qsort. It's probably more suitable to have it like this. It actually doesn't matter, but it is easier to do it like this. Okay, so if n equals 1, okay, if L is less than or equal to R, then return. Then we do qsort. No. What we do partition int pivot partition ALR. Значит, qsort ALL pivot -1, and then you do A pivot +1 and R. That's it. So now we're gonna do partition function. Partition int L and R. So what we do during partition, we just first pick pivot element. We do that on random. Okay, so rand is the function that generates random number. This is not best random generator in the C++, and moreover, taking like this r minus l plus 1, so is a bad thing to do because there is a modular bias. So this operation has the bias to some numbers and so on. So this is not ideally I wanna trial the elements, random element from L to R. Okay. Second. Ideally, you wanna trial the element. Let me write it like this. Let me write it like uh, rand 1 from L to R. I want to take the random element from L to R, or maybe um, from 0 to R minus L plus 1, not included. No. Best practice is to include it, is the inclusion. So I should probably write, okay, let us write like this. You can replace it with another. Okay, let us just 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 know that this is not the best random generator for that. It is only restricted to rand is no more than 2 to the power of 16. So you have a larger array, so you won't be able to generate the random number properly. So if r minus l is too large, r minus l plus 1. I mean, exactly this one. There are functions like arc for random and different random generators. Modulo r minus l plus 1. Okay. And then plus l maybe. Yeah, plus l. Yeah, from l to r minus l. Okay. I'm taking the pivot element and then create the pointer for the pivot for the left part, and then do, no, not while, but for, iterate over left, from left to right, right not included. Maybe it is more convenient to see this instead of strictly less. Okay, j not less than or equal to r minus 1. I do if aj is less than the pivot. I can say either strictly less or not strictly less. It depends on which part is containing the elements equal to pivot. It can be either to the right or to the left. If you write, it's better maybe to write it like left part would be of numbers that are strict less. That way it would make less swaps. But okay, let us stick with what we've agreed already. I plus plus and um, swapping the elements number a of I, position I with position j. That's it. And at the end, I just, I should have, no, that is not int p equals this. So I just remember random element position, and I should put it at the end, as you remember, so that it would not interfere with our for loops. AP and R, okay. Okay, pivot is AR, and then if, yeah, now we do arrangement, and finally at the end, what we do is swapping the last elements, like AI plus 1 elements, next to the end of the block, next to the end of the left block, with the last elements in the array, in the range, and then return I plus 1. G of Q. Merge sort, it says. No, it's not mesh, it's Q sort. Okay, tons of errors, of course. This is not necessary here. What are you not satisfied with? Void, this is not, oh yeah, this is integer function. Integer valued function and qsort n, there's no such function. Okay, maybe we should write qsort 0 to n minus 1 here. Yeah, it works. It is not showing how internal qsort works, but the output is working. Okay, that's it. We are done. You should solve the problems. You should solve the problems from the laboratory work. We are done for today. Have a good day. Goodbye.